నమస్కారం. ఈ రోజు మనము డెఫినేషన్ ఆఫ్ సబ్సీక్వెన్స్, ఎగ్జాంపుల్స్ ఆఫ్ సబ్సీక్వెన్స్, సమ్ బేసిక్ థియరమ్స్ అండ్ సబ్సీక్వెన్సెస్ గురించి తెలుసుకోబోతున్నాం. నా దీనికి బేసిక్గా ముందుగా మనం వాట్ ఈస్ ద డెఫినేషన్ ఆఫ్ సీక్వెన్స్, వాట్ ఆర్ ద ఎగ్జాంపుల్స్ ఆఫ్ సీక్వెన్స్, వాట్ ఈస్ ద కన్వర్జెంట్ ఆఫ్ సీక్వెన్స్, వాట్ ఈస్ ద లిమిట్ ఆఫ్ సీక్వెన్స్, వాట్ ఈస్ ద లిమిట్ పాయింట్ ఆఫ్ సీక్వెన్స్. వీ హ్యావ్ టు డిస్కస్ దోస్ definitions and monotone sequence, increasing sequence, decreasing sequence గురించి కూడా తెలుసుకోబోతున్నాం. సపోజ్ మనం క్లాస్లో రూల్ నెంబర్స్ పిలిచేటప్పుడు 1 2 3 అని పిలుచుకుంటూ వెళ్తాం. అంటే ఏవైనా లెక్కించేటప్పుడు 1 2 3 4 సో ఆన్ అంటే లెక్కించటకు ఉపయోగించే సంఖ్యలనే సహజ సంఖ్యలు అని అంటారు. విచ్ నెంబర్స్ ఆర్ యూజ్డ్ టు కౌంటింగ్, సచ్ నెంబర్స్ ఆర్ కాల్డ్ natural numbers. Set of all natural numbers is denoted by n. N means set of all natural numbers 1 2 3 4 so on. Suppose 1 2 3 4 n here is the r. S is a mapping from n to r. Suppose if S is mapping from n to r, here's 1, 1 by 2, 1 by 3, 1 by 4, so on. Suppose 1 goes to 1, 2 goes to 1 by 2, 3 goes to 1 by 3, 4 goes to 1 by 4. In this way, similarly, n goes to 1 by n, so on. Now here, S is the function, n is the domain, r is the codomain of this function S. Here image of 1 is 1, image of 2 is 1 by 2, image of 3 is 1 by 3, so on, which is denoted by S of 1 is equal to 1, S of 2 is equal to 1 by 2, S of 3 is equal to 1 by 3, so on. S of n is equal to 1 by n, so on. Now S of 1 is denoted by here S1, S2, S3, so on, Sn, so on. Now this is a function, S is a function from n to r. Here these are the values of the function S. In this case here S1, S2, S3, so on. This is a S1, S2, S3, so on. These are range of this function. Now here in this case this is called sequence of real numbers. Sequence nothing but a function from n to r. Here this is called sequence of real numbers. Suppose here if you take here set of all functions, then this function is said to be sequence of functions. Here suppose if in this case today we learn about r, sequence of real numbers. So codomain is r, S1, S2, S3, so on is sequence of real numbers. Suppose here if you take 0, then also we can define here 0 to 1, 1 to 1 by 2, 2 to 1 by 3, 3 to 1 by 4, so on, n to 1 by n plus 1, so on. Here domain 0 is added to the domain. Suppose if you take -1, -2 also. So therefore sequence is a mapping from n to r, or sequence is mapping from w to r, or sequence is mapping from some starting elements from -1, -2, -1, so on also. Therefore sequence is nothing but a function whose domain is n belongs to z such that n greater than or equal to m, where m is also integer. Here z is set of all integer numbers. In this case Sn is said to be sequence. Here this S1 is called first term of the sequence, S2 is called second term of the sequence, S3 is called third term of the sequence, so on. Sn is called nth term of the sequence. Sn is called nth term of this sequence. Now sequence is a function whose domain is set of the form n belongs to Z such that n greater than or equal to m, here m is usually 1 or 0, means we can take m is equal to -2, -3, -4, so on also. In generally here the sequence is denoted by here Sn, n is equal to m to infinity, means first one is Sm plus 1, so on. Suppose if we take m is equal to 1, then first term is S1, S2, so on. These are the terms of the sequence if m is equal to 1. Means Sn, n is equal to m to infinity, or Sm plus 1, Sm plus 2, so on. If m is equal to 1, we may write Sn of n belongs to n, or S1, S2, S3, so on. That means this sequence can be written as Sn of n belongs to n set of all natural numbers. Here n means set of all natural numbers. Suppose Sn is equal to -1 whole to the power of n such that n belongs to n. This is the one sequence. Sn is equal to, suppose 1 by n square, n belongs to n. This is also another example of the sequence. See here Sn is equal to -1 whole to the power of n such that n belongs to n, means first term is here S1 is -1, S2 is 1, S3 is -1, S4 is 1, so on. We can represent terms of the sequence on the real line. Suppose this is a real line R. So if we take this 0, -1, 1, -1, first term S1 is -1, second term is 1, third term is -1, fourth term is 1, so on. Here terms are infinitely many terms are there, but here values are only two values, two distinct values. Suppose another example, we take another example, Sn is equal to 1 by n square or n square, anything, n belongs to n. Now we can represent these terms values on the real line R. First term is, suppose if you take 0, here 1, first term is 1, second term is 1 by 4, third term is 1 by 9, so on. Next fourth term is 1 by 16, so on. Now we have to discuss convergence of a sequence. This is a very, very important concept in the real analysis. Suppose Sn is equal to -1 whole to the power of n by n, n belongs to n is a one sequence of real numbers. Here first term is -1, second term is 1 by 2, third term is -1 by 3, fourth term is 1 by 4, so on. We can represent these terms on the real line, or suppose this is 0, so -1, suppose if you take 1, first term is -1, this is S1, first term, second term is 1 by 2, so 1 by 2, third term is -1 by 3, so here -1 by 3, fourth term is 1 by 4, fifth term is -1 by 5, sixth term is 1 by 6, so on. Here in this case all terms are slowly move to 0. Suppose if you take any number, suppose here 2, if you take one epsilon neighborhood of 2, this epsilon neighborhood of 2 is, so 2 minus epsilon, suppose 2 plus epsilon, this is the one neighborhood of 2. In this neighborhood there are no terms of the sequence. In this neighborhood there are no terms of these sequences. Suppose if you take here 1, in this neighborhood there are no terms of the sequence. Suppose if you take 1 by 2, suppose if you take this neighborhood of 1 by 2, epsilon neighborhood of 1 by 2, in this neighborhood only S2 is in this neighborhood. Therefore this neighborhood has only one term of this sequence. Now here 1 by 4, suppose if you take small neighborhood, in this neighborhood only one term is there, that is the fourth term. Similarly, so on. Here also, suppose if you take minus 1, in this neighborhood, only S1 is in here, this neighborhood, so on. Now, suppose if you take 0, take neighborhood of 0, in this neighborhood, 1 is not here, 1 by 2 is not here, 1 by 4 not here, so on. But here, except some terms, remaining all terms are in this neighborhood. కొన్ని టర్మ్స్ కాకుండా మిగిలిన టర్మ్స్ అన్ని జీరో నైబర్హుడ్ లో ఉన్నాయి. ఎవ్రీ నైబర్హుడ్ ఆఫ్ జీరో హ్యాస్ ఆల్ టర్మ్స్ ఆఫ్ ద సీక్వెన్స్ ఎక్సెప్ట్ ఫైనైట్లీ మెనీ. ఎవ్రీ నైబర్హుడ్ ఆఫ్ జీరో హ్యాస్ ఆల్ టర్మ్స్ ఆఫ్ ద సీక్వెన్స్ ఎక్సెప్ట్ ఫైనైట్లీ మెనీ. So in this case, the sequence Sn is converges to 0. Here 0 is said to be limit of this sequence Sn. How can we define the definition in general way? Suppose Sn is a sequence Sn is said to be converges to a real number yes. Suppose if you take this S. Now we have to take the epsilon neighborhood, S minus epsilon, S plus epsilon. దీనిలో ఎలా ఉండాలి? కొన్ని టర్మ్స్ వదిలేస్తే మిగిలిన టర్మ్స్ అన్ని దీనిలో ఉండాలి. This neighborhood has all terms of the sequence except finitely many. That means all the terms Sn belongs to in this interval S minus epsilon, S plus epsilon. But finitely many, కొన్ని తప్పించి అంటే suppose for all some n greater than n, where n is some real number, ఒక రియల్ నెంబర్ కంటే ఎక్కువ ఉన్న n. So that means there exists a number n such that Sn belongs to S minus epsilon, S plus epsilon. So a sequence Sn is converges to S if for each epsilon greater than 0, అంటే ప్రతి నైబర్హుడ్ కి there exists a number n such that here n greater than n కొన్ని తప్పించి, that implies Sn belongs to S minus epsilon, S plus epsilon. Means in this case here S minus epsilon less than Sn less than S plus epsilon. So here minus epsilon less than Sn minus S less than epsilon. So it can be expressed as in the way mod of Sn minus S less than epsilon. So that implies for each epsilon greater than 0, there exists a number n such that n greater than n, that implies mod Sn minus S less than epsilon. In this case, the sequence is said to be sequence converges to S. Here S is called the limit of the sequence Sn. In this case, we can write as if Sn converges to S, it can be written as Sn converges to S as n tends to infinity, or it can be written in the form of limit Sn n tends to infinity is equal to S. This means limit n tends to infinity Sn is equal to S means the sequence Sn converges to S, or S is said to be limit of the sequence Sn. A sequence Sn of real numbers is said to converges to the real number S, provided that for each epsilon greater than 0, there exists a number n such that n greater than n, that implies mod Sn minus S less than epsilon. If Sn converges to S, we will write limit n tends to infinity Sn is equal to S, or Sn tends to S as n tends to infinity. If Sn converges to S, then S is called limit of the sequence Sn. Suppose Sn is equal to, by previous example, Sn is equal to minus 1 whole to the power of n by n. ఈ సీక్వెన్స్ దేనికి కన్వర్జెస్ అవుతుంది అని చెక్ చేసేటప్పుడు, సపోజ్ బై ద ప్రీవియస్ వన్ So 0, suppose here 0, 1, minus 1. What is the first term? S1 is minus 1, S2 is 1 by 2, S3 is minus 1 by 3, S4 is equal to 1 by 4, so on. First term is minus 1, second term 1 by 2, third term minus 1 by 3, fourth term 1 by 4, so on. Is it converges to 2? If Sn converges to, by definition, if Sn converges to S, then S need not be a term of the sequence. Sn is a sequence of term కావాల్సిన అవసరము లేదు. Now here 2 is not a term of the sequence, but Sn sequence 2 కి కన్వర్జెస్ అవుతుందా కాదా అని చెక్ చేసేటప్పుడు కన్వర్జెస్ కావాలంటే 2 కి ఒక నైబర్హుడ్ తీసుకున్నప్పుడు ఎప్సిలాన్ నైబర్హుడ్ 2 మైనస్ ఎప్సిలాన్ 2 ప్లస్ ఎప్సిలాన్ స్మాల్ నైబర్హుడ్, దీనిలో కొన్ని టర్మ్స్ కాకుండా అన్ని టర్మ్స్ ఉండాలి. ఈ సీక్వెన్స్ యొక్క టర్మ్స్ కొన్ని కాకుండా అన్ని ఉండాలి. ఇందులో ఈ సీక్వెన్స్ యొక్క టర్మ్స్ ఏవీ లేవు. సో దేర్ఫోర్ దిస్ సీక్వెన్స్ డస్ నాట్ కన్వర్జెస్ టు 2. Suppose if you take another one 3, for 3 also same conclusion, there is no term of the sequence in this neighborhood, hence this sequence does not converges to 3. Similarly for minus 2, minus 3, so on also. We discuss at 1, at minus 1, suppose at minus 1, దీనికి ఒక నైబర్హుడ్ తీసుకున్నాం. దిస్ ఇస్ ద minus 1 minus epsilon minus 1 plus epsilon small neighborhood. ఈ నైబర్హుడ్ లో ఈ సీక్వెన్స్ అనేది మైనస్ 1 కి కన్వర్జెంట్ కావాలంటే ఈ మైనస్ 1 యొక్క ఈ స్మాల్ నైబర్హుడ్ లో కొన్ని కాకుండా అన్ని ఉండాలి, కొన్ని టర్మ్స్ కాకుండా. ఇందులో ఒకే ఒక టర్మ్ ఉంది. దీని ప్రకారంగా ఒకే ఒక టర్మ్ ఉందంటే therefore Sn does not converge to minus 1. Similarly for minus 3, 1 by 4, 1 by 2 also same. At 0, suppose take at 0, in this neighborhood 1 by 4, next term is minus 1 by 5, so on. All terms are closely moved to 0. So every neighborhood of 0 has all terms of the sequence except finitely many. కొన్ని టర్మ్స్ కాకుండా అన్ని టర్మ్స్ 1 by 6, here minus 1 by 5, so on. అన్ని టర్మ్స్ దీనిలో ఉన్నాయి. Therefore this sequence converges to 0. So in this case 0 is said to be limit of the sequence Sn. Now we discuss about increasing sequence and decreasing sequence also. Suppose Sn is a sequence of real numbers S1, S2, S3, S4, so on. These are terms of the sequence Sn. If S1 కంటే S2 ఎక్కువ, S2 కంటే S3 ఎక్కువ, S3 కంటే S4 ఎక్కువ, so on. ఈ విధంగా ఉన్నట్లయితే this sequence is called increasing sequence. టర్మ్స్ విలువలు కనుక పెరుగుతూ ఉంటే దిస్ సీక్వెన్స్ ఈజ్ కాల్డ్ ఇంక్రీజింగ్ సీక్వెన్స్. ఇఫ్ ఒకవేళ S1, S2, S3, S4, సో ఆన్ అంటే ఇవి తక్కువగా ఉన్నట్లయితే, టర్మ్స్ యొక్క విలువలు తగ్గుతూ ఉన్నట్లయితే దెన్ ది సీక్వెన్స్ ఈజ్ సెడ్ టు బి డిక్రీజింగ్ సీక్వెన్స్. సపోజ్ ఇన్ దిస్ కేస్ వీ కెన్ రైట్ యాజ్ ఇన్ జనరలైజేషన్ Sn, సపోజ్ ఇఫ్ టేక్ Sn ప్లస్ 1, దీనిలో టర్మ్స్ యొక్క విలువలు పెరుగుతూ ఉన్నాయి కాబట్టి Sn less than or equal to Sn plus 1 for all n. Here in this case Sn greater than or equal to Sn plus 1 for all n. ఈ విధంగా ఉన్నట్లయితే సీక్వెన్స్ Sn ని ఇంక్రీజింగ్ సీక్వెన్స్ అని, ఈ విధంగా ఉన్నట్లయితే సీక్వెన్స్ Sn ని డిక్రీజింగ్ సీక్వెన్స్ అని అంటారు. సపోజ్ Sn is equal to n square, n belongs to n. This is the one sequence of real numbers. S1 is 1, S2 is 4, S3 is 9, so on. Values are increasing, therefore this sequence is increasing sequence. Or in generalization, here n square and n plus 1 square which is less than, therefore Sn less than Sn plus 1, therefore increasing sequence. If strictly increasing is there, then this type of sequence is said to be strictly increasing sequence. Now suppose if you take Sn is equal to 1 by n, here n is less than n plus 1, that implies 1 by n is greater than 1 by n plus 1, that implies 1 by n means here Sn which is greater than Sn plus 1. Here values are decreasing, therefore this sequence is said to be decreasing sequence. If the symbol is strictly greater than, then this sequence is said to be strictly decreasing sequence. So a sequence S of real numbers is an increasing sequence if Sn less than or equal to Sn plus 1 for all n, a decreasing sequence if Sn greater than or equal to Sn plus 1 for all n. Suppose ఏదైనా ఒక సీక్వెన్స్ either increasing or decreasing, ఇంక్రీజింగ్ కానీ లేదా డిక్రీజింగ్ కానీ అయితే, then that sequence is said to be monotonic sequence. Monotonic sequence or monotone sequence. A sequence is said to be monotone sequence or monotonic sequence if this is either increasing or decreasing. Now we discussed about subsequence of a sequence. This is important concept in the analysis. Suppose Sn n belongs to n is a sequence of real numbers. So first term is S1, second term is S2, S3, S4, so on. Suppose if you take S5, so on. దీనిలో in this sequence there are infinitely many terms are there. Infinitely many terms. Now we can take infinitely many terms from this one. So S1, S3, S5, S7, so on. Now these are also infinitely many terms from this sequence. Here these terms preserve the order, so on. That means here 1, 3, 5, 7 subscripts there. Here 1 is strictly less than, 3 strictly less than, 5 strictly less than, 7, so on. Now here suppose S2, S4, S6, so on. These are also infinitely many terms from this sequence. Here subscripts are 2, 4, 6, so on. 2 less than, 4 less than, 6 less than, so on. Now in this case these terms is said to be a subsequence of this sequence. Here also these terms is said to be subsequence of a sequence Sn, n belongs to n. Now suppose if you take S1, S2, S6, S10, S11, S14, S17, S20, suppose so on. This is also a subsequence. Since here these are preserved in order 1, 2, 6, 10, 11, so on. Here 1 less than, 2 less than, 6 less than, 10 less than, 11 less than, 14 less than, so on. So this is also a one subsequence of this sequence Sn. Now suppose if you take here S4, S8, S6, S10, S12, S14, S16, suppose so on. Here subscripts 4, 8, 6, 10, so on. 4 less than 8, here 6, which is not less than 6. Hence this is not a subsequence of this sequence. This is not a subsequence. So what is the definition of subsequence? First of all, we take the subscripts. Suppose this is one subsequence. This is considered as S1. 1 is n1, this is n2, suppose this is n3, this is n4, this is n5, so on. Subscripts is strictly increasing, so n1 less than n2 less than n3 less than n4 less than so on. So these are the positive integers. So n1, n2, n3, these are the positive integers which is strictly increasing. Therefore, here nk is sequence of positive integers or natural numbers, sequence of integers or natural numbers. Here k belongs to n, but here strictly increasing. Nk is strictly increasing sequence of positive integer. Then here the terms Sn1, Sn2, Sn3, Sn4, so on. This is the subsequence of this sequence. So therefore, here Snk is subsequence of this sequence where k belongs to n. Nothing but here subsequence is also a sequence. It contains infinitely many terms and preserves the order. దీనిలో మనం ఏం తీసుకోవాలి, ఇందులో నుంచి infinitely many terms తీసుకోవాలి, but preserves the order. So therefore, this is called subsequence of this sequence Sn. Suppose Sn n belongs to n is a sequence, let nk k belongs to n is a sequence of positive integers which is strictly increasing such that n1 less than n2 less than so on, nk less than nk plus 1, so on. In this case, Snk is said to be subsequence of sequence Sn. That means here what? Snk is a just selection of infinite terms of sequence Sn taken in order. Snk is a just selection of infinite terms of sequence Sn taken in order. ఈ సీక్వెన్స్ ఆఫ్ టర్మ్స్ లో ఇన్ఫినిట్లీ మెనీ టర్మ్స్ ఉన్నప్పుడు దీని నుంచి కూడా ఇన్ఫినిట్లీ మెనీ టర్మ్స్ తీసుకొని ఆర్డర్ ని ప్రిజర్వ్ చేసుకుంటూ ఉండాలి. ఆర్డర్ కనుక రివర్స్ అయితే దట్ ఈస్ నాట్ ఏ సబ్ సీక్వెన్స్. Suppose we can discuss about the examples of subsequence. Suppose Sn is equal to n square minus 1 whole to the power of n, n belongs to n. Now here first term S1 is minus 1, S2 is 4, S3 is minus 9, S4 is 16, so on. Now we can take in order first term, third term, fifth term, so on, S1, S3, S5, so on. That means here 1 less than, 3 less than, 5, so on. So here S1 means here minus 1, minus 9, so on. This is also a one subsequence of this sequence Sn. దీనిలో subsequence కావాలంటే దీంట్లో infinitely many terms తీసుకోవాలి, but they preserve order. Similarly 4, 16, 36, so are also one subsequence. Suppose a sequence Sn converges to S. Sequence Sn converges to S. That means దీనికి ఒక ఎప్సిలాన్ నైబర్హుడ్ తీసుకున్నప్పుడు S మైనస్ ఎప్సిలాన్, S ప్లస్ ఎప్సిలాన్ ఒక నైబర్హుడ్ తీసుకున్నప్పుడు ఈ సీక్వెన్స్ యొక్క టర్మ్స్ కొన్ని తప్పించి అన్ని ఉండాలి, కొన్ని తప్పించి అన్ని ఉండాలి. సపోజ్ ఇక్కడ S1, S2 కొన్ని టర్మ్స్, సపోజ్ S3, S4 కొన్ని టర్మ్స్ లేవనుకుందాం, మిగిలినన్ని దీనిలో ఉండాలి. సో దట్ మీన్స్ S5, S6, S7, S8, so on, all terms must lie in this neighborhood of S. Every neighborhood of S contains all terms of the sequence except finitely many. కొన్ని తప్పించి అన్ని ఉండాలి. Suppose if you take the sequence, subsequence Snk, Sn is a one sequence, Snk is subsequence of this sequence. దీనిలో కూడా ఇన్ఫినిట్లీ మెనీ టర్మ్స్ ఉన్నాయి, కానీ ఆర్డర్ ప్రిజర్వ్ చేసింది. సీక్వెన్స్ యొక్క టర్మ్స్ కొన్ని తప్పించి అన్ని దీనిలో ఉన్నాయంటే సబ్సీక్వెన్స్ యొక్క టర్మ్స్ కూడా కొన్ని తప్పించి అన్ని దీనిలో ఉన్నట్లే. ఇవి కూడా ఇక్కడి నుంచి తీసుకున్నాం కాబట్టి therefore if the sequence Sn converges to S, దేనికైతే కన్వర్జెస్ అవుతుందో అంటే కొన్ని తప్పించి అన్ని దీంట్లో ఉన్నప్పుడు దీనికి కూడా all terms of this Snk must lie in this neighborhood of S except finitely many. Therefore Snk is also converges to S. If Sn converges to S, then every subsequence is also converges to same limit of this sequence S, Sn. So therefore we can conclude that if the sequence Sn converges, then every subsequence converges to the same limit. We can prove this theorem by easily. This is by geometrically we can observe. Suppose let Sn be a sequence if Sn converges to S, that means if Sn converges to S means for each epsilon greater than 0, there exists a number n such that n greater than n, that implies mod Sn minus S less than epsilon. So కొన్ని తప్పించి అన్ని దీనిలో ఉన్నాయి ఒక సీక్వెన్స్ కన్వర్జెంట్ అయినప్పుడు. Suppose if you take Snk with the, now let Snk be subsequence of the sequence Sn. Now we can conclude that here Nk is greater than or equal to always k. Suppose if k is equal to 1, which is always true, n1 is greater than or equal to 1. This is the subscripts here, therefore this is the first term or second term or third term, anything, therefore n1 greater than or equal to 1. Suppose which is true if k minus 1 values, n minus k is greater than or equal to k minus 1. Now here Snk is a subsequence. Subsequence means here nk minus 1 is strictly less than nk, so on. Subsequence means. So which is greater than nk. So k minus 1 is an integer, that means or natural number. This is also natural number. This is also natural number. Which is greater than this one means from this one we can conclude that here k is greater than k minus 1. Which is nk minus 1 is greater than or equal to k minus 1. So nk is strictly greater than k minus 1. From these two relations we can conclude that nk is greater than or equal to k. Here we can conclude that nk greater than or equal to k. From this equation we can observe that if k greater than n, already there is a natural number n, so one number or real number n. If k greater than n, that implies if k greater than n means here nk is also greater than n. If here n greater than n, from this one Sn minus S less than epsilon. So in place of n here nk is there. Therefore from equation 1 we can observe that here Sn is there. Therefore here S nk minus S less than epsilon. So for each epsilon greater than 0, here from these two relations, each epsilon greater than 0, there exists number n such that k greater than n, that implies mod Snk minus S less than epsilon. So this subsequence Sn converges to S. So it can be written as Snk converges to S as k tends to infinity. So we can write here limit Snk k tends to infinity is equal to S. If the sequence Sn converges to S, then subsequence is also converges to S. If a sequence converges to one real number, then every subsequence is also converges to the same limit to S. So this is the one theorem, important theorem in analysis. Now we can discuss another theorem here. what is the dominant, nth term is said to be dominant if Sm less than Sn for all m greater than n. That means, suppose if you take here Sn is equal to 1 by n, Sn is equal to 1 by n, the sequence, first term is 1, second term is 1 by 2, third term is 1 by 3, so on. First term అనేది మిగిలిన టర్మ్స్ కి అన్నిటికంటే కూడా ఇది పెద్దగా ఉంటుంది, which is dominated remaining all terms, remaining coming terms. So here S1 is greater than S2, so mean all terms means S1 greater than Sm for all m greater than 1. So అన్ని టర్మ్స్ కంటే కూడా ఇది ఎక్కువ ఉంటుంది. So this term is said to be dominant. Similarly here S2 is also dominant, since దీని తర్వాత వచ్చే అన్ని టర్మ్స్ కంటే ఇది పెద్దగా ఉంటుంది. So S2 is also dominant term, S3 also dominant term, so on. In this case here every term is dominant in this sequence. So what is the general definition is, nth term is said to be a dominant term of the sequence Sn if Sn is greater than Sm for all m greater than n. Sn అనేది డామినేట్ కావాలి, మిగిలిన టర్మ్స్ కంటే తర్వాత కమింగ్ టర్మ్స్ కంటే ఇది ఎక్కువగా ఉండాలి. Then the term Sn is said to be dominant term in this sequence. Now suppose Sn is a sequence it has maybe infinitely many terms of dominants or finitely many terms of dominants. If it has infinitely many terms of the dominants, suppose arranging list of them in subsets as increasing, so n1, n2, so on. That means here Sn1, Sn2, Sn3, so on. These are the dominant terms in this sequence, and n1 is less than n2 less than n3, so on. Dominant, each term is a dominant means Sn1 is greater than, Sn2 is greater than, Sn3 greater than, so on. So in this case this subsequence Snk is strictly decreasing subsequence. So here in this case Sn has one decreasing subsequence. If suppose a sequence Sn has finitely many dominant terms, similarly we can observe that there is one increasing sequence. So in this case every sequence has a either increasing subsequence or decreasing subsequence. Therefore every sequence has monotone subsequence. Every sequence has monotone subsequence. Suppose let Sn be a sequence which is bounded sequence, and suppose increasing. Bounded means some k1, k2, all terms of the sequence must lie in these two numbers between k1 and k2. So a sequence Sn is said to be a bounded sequence if there exist real numbers k1, k2 such that k1 less than or equal to Sn less than or equal to k2 for all n belongs to n. So in this case the sequence Sn is bounded. So bounded means which is a boundable. Bounded means it has supremum. So suppose if you take this is a supremum is yes. Similarly there is infimum s dash. Now suppose it is increasing sequence. Increasing sequence means వచ్చే వాల్యూ టర్మ్స్ యొక్క విలువలు పెరుగుతూ ఉండాలి. సపోజ్ ఫస్ట్ టర్మ్ ఈజ్ హియర్ S1, నెక్స్ట్ టర్మ్ ఆటోమేటిక్గా ఇటు సైడే ఉంటుంది S2, S3, S4, S5, సో ఆన్. కానీ సుప్రమం S ని మాత్రం దాటి వెళ్ళదు. సో సిన్స్ ఇట్ ఈస్ ద బౌండెడ్. సో దేర్ ఫోర్ అన్ని టర్మ్స్ ఇక్కడ S దగ్గరకు వచ్చి ఆగిపోతాయి ఇక్కడికి. సో ఇఫ్ యు టేక్ ఎనీ నైబర్హుడ్ ఆఫ్ దిస్ S, it has every neighborhood of S has all terms of the sequence except finitely many. Therefore this sequence converges to S. If a bounded sequence is increasing, then which is converges to its supremum. Similarly we can observe that a bounded sequence and which is decreasing, which is converges to infimum. Suppose Sn is a sequence, Sn is bounded sequence, and every sequence has monotone subsequence. Let Snk is monotone subsequence. So which is also bounded, since Sn is bounded. Therefore which is bounded, which is a bounded and monotone subsequence. By previous, every bounded and monotone sequence is converges. So here is a bounded and monotone, therefore which is converges. So Snk is converges to some limit. Yes, if Sn is bounded, it has a monotone sequence, therefore which is also bounded. We know that every bounded monotone sequence is converges, hence Sn has a convergent subsequence. Therefore every bounded sequence has convergent subsequence. This is called, this theorem is Bolzano-Weierstrass theorem. This is also very important in the analysis part. Now every sequence has monotonic subsequence. We can prove this one. Bolzano-Weierstrass theorem is every bounded sequence has a convergent subsequence. Now these are some entrance examination oriented questions. So thank you very much. Thank you.